So here's a comparison between a super heterodyne radio and a tuned radio frequency radio. So AM signals. You have the frequency that you're transmitting at, and it is, you have a modulated signal that goes along that. And as you can see here, the amplitude of that carrier frequency varies as it goes along, hence amplitude modulation. Now that carrier frequency is the same no matter how high the amplitude gets throughout the signal. However, the inherent problem is if you have a circuit that's tuned to receive a single frequency, it only will receive that one frequency. So you need to be able to change the resonance of the circuit to be able to take in and hear the different radio signals from different frequencies. So what we do is, there's two ways that I'm going to explain how it's done: a tuned radio frequency receiver and a super heterodyne receiver. So I'll begin with the tuned radio frequency, or TRF receiver. And the way that works is, essentially, you have an antenna, and that antenna goes into a number of boxes here. I'm drawing them as, because this is a block diagram. And the radio frequency essentially goes into the radio, and you have a series now. A lot of these radios are from like the 1920s, 1930s, and they have a series of big dials in the front. And you have to, there's not really one dial that you go, oh, I want this to be 1100 AM, which is 1100 kilohertz. That didn't exist yet. So what happened is you'd have these three dials, and you had to sort of play this balancing juggling game between all three of them. And what these did is, these are a combination of inductance coils with capacitors called a tank circuit or an LC circuit, which has a resonant frequency to it, as well as an amplification vacuum tube. And what these do is each one in succession amplifies the radio frequency coming through the antenna. So it's at a usable level that the circuit can deal with. So each one of these now, you have to adjust separately, because once the signal comes in, you have to adjust this first one to play well with that frequency. Now this new frequency it's creating, you have to play with that one to get that one to play well, and then so on. But either way, you have now a strong radio frequency that's been still modulated, that's coming out of your radio. And this now goes into a demodulator. This essentially is sometimes called a detector. Works in the same practice as if you have a crystal radio here, which is essentially you have, I'm going to draw this in a modern sense using modern symbols, but we have essentially now, this is the simplest crystal radio circuit you can have. It's an antenna, a ground. I drew chassis ground here, but it could be earth ground either. And you have a rectifier. In this case, I drew it as a diode. It could also be drawn as a cat's whisker, but that's the same thing. It's just an older version of the same device. Anyway, I digress. This circuit here only has four components: the antenna, the ground, the diode or rectifier or demodulator or detector, and the earphones. That's what this symbol means. And basically all this does is it takes the signal in and chops off that one half there, because obviously if you listen to that, it would cancel each other out. So it chops off this one sideband here and demodulates it into its component sound frequencies. And you can hear that through the earphones. That's what this does. This demodulator does essentially the same thing. So it's essentially a rectifier, and it can be done in various different ways. Usually it has some sort of detector crystal or detector diode or something like that. But that's enough for that. And then it goes into an audio amplifier. And that does exactly what you think it does. It just amplifies it enough that when you use it with some period, headphones like these, it has enough oomph to drive that, because those have around 3,000 ohms of impedance. So that's pretty stout. And that's basically how a TRF works. Now, the drawback of this type of thing is, obviously you have to tune it like a million different ways, and it's just all experimentation. And it was so crummy that back in the day, let's say your radio station was broadcasting at 1400 kilocycles, which nowadays we call kilohertz. Like I said, you don't just take a dial and you go, oh, there we go, 1400 kilocycles, boom, we're tuned to that station, WXYZ. No, you had to go through all three of these. You had to set these all the way to the left, and then tune the first one, and then, oh, that's kind of close, let me start using the second one, then use the second one, and the third one, and so on. And then you'd actually just write down the arbitrary numbers that are on all three dials, and just know that WXYZ at 1400 kilocycles is these three numbers on these three dials. And it's not really, conducive to easy operation. So the next type of circuit is called a superheterodyne. And the way this one works is much more interesting. A lot of the superheterodyne was used from the 1930s, which made the TRF completely obsolete. Through, oh my God, most of the 20th century, honestly. And even today, superheterodyne circuits are still being used in radio circuitry, but they're just not done with tubes. They're done with, solid state circuitry. I digress. So, like I said, it's difficult to make a circuit that is tunable to a certain frequency, as we just saw with the previous example. But it's easy to make a circuit that is receptive to one particular frequency. Again, like I mentioned with the example here, that's tuned to one frequency. That's easy to make. So a guy named Edwin Armstrong invented a circuit called the superheterodyne circuit. Now what this does is, if you have let's say you have two speakers and they're playing two different tones. This one's playing 400 hertz and this one's playing 450 hertz. Now, if you listen to them both together, those two waveforms add to each other. And the difference of them, with 50 hertz, you'd hear between the two. So you'd hear this wub, 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 wub at 50 times a second. Edwin Armstrong took that principle and applied it to radio. So the way these work is, you have an antenna, again, but that goes into a mixer. Now, why do we need a mixer for this? Well, glad you asked. You have here I'll draw it as a little knob here, and you have your different tuning things. This is your variable capacitor. And what this does is, the variable capacitor in the tank circuit, which I'll draw that quickly for you, what that looks like. You have a capacitor here, and you have an inductor. Now, oftentimes, that's a variable inductor, or this is a variable capacitor, or both. And basically, if you change the inductance value, or the capacitance value, or both, you change the resonant frequency of that particular circuit. Now, like I said, it's called a tank circuit, because it kind of fills up and empties like a tank. That's why. Or it's LC for inductance, capacitance, but either way. So this variable capacitor changes its capacitance in conjunction with a vacuum tube here. Now, this vacuum tube is what we call a pentagrid converter tube. And what this pentagrid converter tube does, with a change in capacitance with this variable capacitor, it changes the oscillating frequency of that circuit here, just like a tank circuit. And in some ways, it kind of is. So it adds this frequency up to, with this frequency that it's receiving from the air. Now, each superheterodyne radio will have marked on it IF for intermediate frequency. My personal super heterodyne radio, 1941 Ward's Airline 14BR112A, rolls right off the tongue, has a intermediate frequency of 455 kilocycles, or nowadays we call it kilohertz, but kilocycles is what they said back then. So what I'm getting to with all of this is it's hard to make a circuit that listens to different frequencies, but it's easy, again, to make one that listens to one. So why don't we make it listen to one? We have a filter that's looking for 455 kilocycles. But then how do we tune it? Again, beats. Like I mentioned with the two speakers. Whatever you take through the antenna, we add it to this particular frequency that we're generating from this oscillator. And by changing the frequency that we're generating through this, the difference between this and this becomes 455 kilocycles away from the desired listening frequency. You get where I'm going with this? Instead of changing what frequency we're listening to, we're just changing this frequency, using this frequency to this frequency. And we're just listening through that through the filter. Now this filter then outputs it to some RF amps. And that then goes to a demodulator. Again, same deal as the other one. You have some rectifiers, some detector circuitry in there that just takes that AM waveform and brings it into an audio waveform. Then you have audio amplifier. And yes, you guessed it. What's next? A speaker. So I'll go over this again. TRF, tuned radio frequency circuit. What this does is it takes the signal in and it's trying to listen to a certain frequency, which is difficult, which is like, as you can see here, you have a whole bunch of these various knobs you have to turn to get a certain frequency to come through the radio. So you have 3 tuned radio frequency circuits here, and then it goes through a demodulator and then through an audio amp, and you can listen to it. The super heterodyne, the antenna brings the RF in. You have an oscillator circuit, and this oscillator circuit is added, the frequency created with this is added to the frequency that's coming in through the antenna. And we're trying to add a specific frequency to get to be the intermediate frequency, in this case 455 kilohertz or kilocycles. And then once we listen to that, we boost the RF frequency, demodulate it, boost the audio level, and then boom, we listen to it. Clear as mud? Great.